This comes out of section 8.4, derivatives of log functions. Earlier sections of this chapter that y equals e to the x, an exponential growth function with the base e, has the derivative of y equals e to the x, which is pretty unusual, which is pretty much the main thing that makes e such a special number, why we would bother using such a number as 2.71828, etc., etc. What I want to do now is look at the inverse of that function. So in other words, x equals e to the y. That can also be written as y equals log base e of x, or in other words, ln of x. But let's look at it this way for a second. If I take the derivative of this implicitly with respect to x, I'll get that 1 equals e to the y times y prime. And if I solve that, I get y prime equals 1 over e to the y. Since up above here I see that e to the y is equal to x, I can also say that y prime equals 1 over x. And so without doing too hardcore proof there, we've basically shown one of the important things that you have on your formula sheet that says if you have the function y equals ln x, the derivative of that is 1 over x. And it allows us actually a surprising amount of power, I guess, in taking derivatives. Let's start off with some classic just practice examples where we're taking the derivatives to differentiate this function y equals x cubed times ln x. Well, now that we know that the derivative of ln x is 1 over x, we could just do this with the product rule and say, okay, y prime equals the first function times the derivative of the second plus the second function times the derivative of the first. Now, that's an expression. If they just gave us a number for x, we could just put in a number there, but we can simplify that a little bit to say that y prime equals x squared plus 3x squared ln x, and even better to factor out that x squared and say we've got 1 plus 3 ln x. That would be, a good enough derivative that you could find critical numbers and do things with it if you're asked to do so. So the next practice example of this that I want to try is differentiate this one. Y equals the natural log of x squared plus 6x minus 7. Now, that function, a lot of people make the mistake of starting to try to distribute this natural log into those brackets somehow. It's the natural log of that whole entity. So the derivative of it is going to start off with 1 over that, and then multiplied by the derivative of the inside, which is just 2x plus 6. So it's kind of a classic chain rule situation. If I put that all together, I can see that it'll be 2 times x plus 3. Try factoring it, see if anything cancels. And then on the bottom here, what do I have? I have x plus 7, x minus 1. So no factors cancel, but at least if I were to use that derivative for something else, I would have a nice factor derivative. In general, the chain rule basically says that if you have the natural log of a function, the derivative of that is going to be 1 over the function times the derivative of the inside function. So even nicer, you can write it as g prime of x over g of x. And we use that chain rule for natural logs quite often, and actually as the section goes on, as the chapter goes on, to our advantage to take derivatives of very, very complicated functions.